Hi guys, welcome to this set of videos, and what we're going to do here in this set of videos is they'll follow along with everything out of your book from Chapter 7, Section 4. Now what we've been doing here in Chapter 7 is taking a look at exponential and logarithmic functions, and what we're going to do now specifically here in Section 4 is this set of notes will help us work our way through solving logarithmic equations and inequalities. And before we go ahead and get started with that, I'll first remind you that we started the chapter by looking at the graphs of exponentials, and then we looked at solving exponential equations and inequalities. Then in section 3 of this chapter, we looked at graphing logarithmic functions, which are just the inverse of the exponential. And so now here in section 4, we'll look at solving logarithmic equations and inequalities. Let's start with a couple of objectives or learning targets to kind of help us focus as we make our way through this set of notes, and that's exactly what our objectives are. You are going to start off by solving logarithmic equations, and then we'll move on to solving logarithmic inequalities. You'll see a lot of parallels here between what we did when solving exponential equations and exponential inequalities. In fact, we use that equality property of exponential functions. Well, it turns out we have an equality property for logarithmic functions, and they look almost identical. It's just now we're doing logarithms instead of exponentials. But I want to remind you how exponentials and logarithms are tied together. So remember what we said about exponentials and logarithms. If you have x, oh, sorry, hold up, that's my highlighter. If you have x is equal to b raised to the y power, right? This is an exponential function where x is equal to some base, right? It can be a number, or it is a number, b is a constant, raised to some power where y is a variable. Well, what we said, right, this is an exponential function, what we said is that the logarithm, by definition, is the power, right? What I'm asking you to do when I ask you to take a logarithm is I'm asking you to figure out what does that exponent need to be so that b raised to that exponent gets me x. And so we call y the logarithm of x, because the inverse, in order to solve this guy for y, we would simply take the log base b, since the base of my exponential is b, the base of my logarithm would be b. And when I take the log base b of x, what I'm going to get is y, right? These are inverse functions, right? This one is saying b to the y power gets me x. This one is saying log base b of x gets me y, right? This is if I don't know what that exponent is, if I don't know y, okay, fine, I can solve for y, figure out what y is by taking a logarithm. Take the log base b of x, and that'll tell me what that power needs to be. Here's really sort of the takeaway. Logarithms are just exponents. When you're taking a logarithm, you're trying to figure out what is that exponent. What does that exponent need to be in order to make this equation true? Right? That's what we're going to be doing. Also, we stated that exponentials and logarithms are inverse functions. All right? Exponentials and logarithms are inverse functions, which I, again, briefly mentioned right here. Inverse functions. Oh, nope, I want my yellow highlighter, not that one. Inverse functions will always undo each other. We saw that when we spent a lot of time on inverse functions a chapter or two ago. When you do the composite functions, f of g of x or g of f of x, you'll remember that those were written this way. I could do f of g of x or g of f of x, right? Either one of those composite functions, both of which I have written here, right? This one is f of g of x. This one's g of f of x, right? They mean the exact same thing. It's just slightly different notation. But we talked about the fact that you're going to have inverse functions, or if you have inverse functions and you do the composite of those inverse functions, either f of g of x or g of f of x, what's going to happen is the inverse functions undo each other. They cancel each other out, and you're left with just an x, which is exactly what's going to happen here for exponentials and logarithms. Let me show you. I have f of x, which is an exponential, b to the x. I have g of x, which is the logarithm, log base b of x. Now, if I go ahead and do the composite function, right, I'm going to plug g of x into f of x. So g of x is log base b of x. I'm going to plug that into f of x, right? So this log base b of x will go into f of x everywhere I have an x. Well, there's my x, right? It's b raised to the x power. So my composite function would be the base b, and then that exponent is going to be g of x, log base b of x. But we talked about this before. We said if ever the base of the logarithm and the base of the exponential are the same, they'll cancel each other out. Just like with radicals, if you square something that you're taking the square root of, the square and the square root cancel. Or if you cube something you're taking a cubed root of. If the index and the power are the same, they cancel each other out. Same is true here for exponentials and logarithms. If the base and the exponential base, if the base of the logarithm and the base of the exponential are the same, they'll cancel each other out, and I'm left with just that x. Same thing down here if I do g of f of x. I'm going to take f of x, which is the b of x. There it is, f of x, it's b of x. I'm going to plug it into g of x. I'll plug b of x in everywhere I have an x in g of x. Right? So my g of x is log base b of x. I'm going to plug f of x in right there for that x, which is what I did. There's my log base b of x, but instead of x, I plug in f of x, which is b of x. And again, same thing we saw above. If the base of the logarithm and what you're taking the logarithm of, the base of the exponential, if those are the same number, they'll cancel each other out, and you're left with just an x. All right, so the idea here is this. Logarithms are just exponents. When you're taking a logarithm, you're figuring out what is the exponent. And exponential functions and logarithmic functions are inverses. Now, some of the stuff that we're going to do with it, well, I'd like you to go ahead and, I say solve, it's not really solving. I want you to evaluate the following logarithmic expressions. I've got a couple of them here for you. Let me slide this over a little bit just so that I have some room. Now, there's a couple of ways to do these, and I'll show you all of those options. So let me quickly just right up here split this up a little bit. We have option 1, option 2, and option number 3. You got 3 different options. I don't care which way you want to do it. It's totally up to you. In fact, being comfortable with all of them is really not that bad of an idea. It's a pretty good idea to be comfortable with all of them. First of all, option number 1 is if you have a calculator with the math print on it, then you're going to do that function in your graphing calculator, the log base function. It should be under the math menu. You have a button on the left-hand side of your graphing calculator that says math on it. Just go into that menu, scroll down until you find log base. This will be the change of base function in your graphing calculator. Your graphing calculator will then allow you to enter log base 2 of 64. And so if you just go ahead and do that right in your calculator, log base 2 of 64, here's what it's asking you to find. It wants to know what power does 2 need to be raised in order to get 64. Well, obviously 2 to the 6th power is 64. So your calculator will tell you the log base 2 of 64 is 6. If I do 2 raised to the 6th power, because remember, a logarithm is an exponent, right? I am finding the exponent. 2 raised to the 6th power is 64, right? So that's the first option. You could just use your calculator. The second option is if you don't have the graphing calculator and you don't have that log base function, you'll use the change of base formula. Remember the way that worked. Since this is a log base 2, you can't use the log button on your calculator because that's a log base 10. So we'll just simply convert all of these to a log base 10 expression, and we'll do it using the change of base formula. And remember the way it works. I'll take the log of 64, so this would be a log base 10, so log of 64. Now you can use the log button right on your calculator because that's the base isn't written, it's an implied 10, so log base 10 of 64 divided by log base 10 of 2. And if you use that change of base formula, which you certainly is a perfectly good option, it's a really, really good one, log of 64 divided by log of 2, and your calculator again will tell you, hey, that's equal to 6. But let's say you didn't have your calculator with you. Okay, no problem. We've got a fantastic method that will allow us to do this without a calculator. We call it the Snail Method. Remember the way the Snail Method works. The way the Snail Method works is you start with the base and you work your way around the equal sign, converting the logarithm into an exponential. So it'll be 2 raised to the y power is equal to 64. So we'll have 2 raised to the y power is equal to 64. But then, right, 2 raised to the y power is equal to 64. We have that property of exponential equations that tells me if the bases are the same, I set the exponents equal to each other. Well, it doesn't require a whole lot of work to figure out 64 is 2 to the 6th power. So I can rewrite this as 2y is equal to 2 to the 6th power. And again, because the bases are the same, the property tells me I set the exponents equal to each other. Then I know that y is equal to 6. So 3 different methods. All 3 methods give me the exact same answer. Doesn't matter which way you want to do it. I'll do all 3 for all of these examples. So let's go ahead and do the next one. Slide up here a little bit, and here we go. First off, log base 3 of 81. Again, if you've got the graphing calculator that'll do it, you can just simply do the change of the log base function on your graphing calculator. And again, what this will tell you is I want to know to what power must I raise 3 to get 81. And of course, the answer is 4. 3 to the 4th power is 81. If you don't have the log base on your calculator, you just do the change of base. We'll do the log, hit log of 81 divided by the log of 3. Again, that's just the log button on your calculator. We call it change of base because you're changing it from the log base 3 to now log base 10, which every calculator has a log base 10 button on it. Log 81 divided by log of 3, and shouldn't surprise you any, your calculator will tell you the answer is 4. Or if you don't have your calculator, no big deal. Snail method. Snail your way around that equal sign. 3 to the y is equal to 81. Again, doesn't take a whole lot of work to figure out that 81 is 3 to the 4th. If the bases are the same, the property tells me I set the exponents equal to each other. Y is equal to 4. And either way, any of the 3 options, you're going to get 4 every single time. I got one more for you here. Let's do it all 3 ways. Again, if you've got the log base function on your graphing calculator, fantastic. Plug it in. What you're looking to do is figure out what power do I need to raise the 4 to, right? What is the power, the exponent on the 4, need to be in order to get 256? Of course, the answer is 4. 4 to the 4th power is 256. If you don't have the log base function on your graphing calculator, that's okay. Every calculator has a log base 10 button. So we'll do log of 256 divided by the log of 4. And your calculator will simply give you a 4, right? So the change of base formula works for every calculator if you don't have a fancy graphing one. Or if you don't have a calculator at all, no big deal. Snail method. Do our little snail method. In fact, here, let me draw my little guy because these snails are so cute. Remember, we would like to name our snail Gary, and Gary likes to Gary the snail, he leaves his little trail of green sludge behind him. So slippery. Anyway, Snail Method, and what it does is it allows me to rewrite this guy as 4 to the y is equal to 256. And again, it wouldn't take you very long to figure out 256 can be rewritten as 4 to the 4th. Again, because the bases are the same, the property tells me I can set the exponents equal to each other, and we get y is equal to 4. Okay guys, a great review of exponentials and logarithms, how they tie together, and several different options you have for evaluating logarithms. Please be comfortable with all of them. But if you find one you like a lot, feel free to use it. Head on over to the next page of the notes and we'll try solving a few more problems. I'll meet you guys over there.